Greetings, friends. We are here for our final class of the week, and we'll get started off. Just a quick reminder on PLC 13. That is your review, your final exam review, final celebration review, traffic light. Homework 8 is up and running. That is due in a week. That's due next Thursday, which is the 14th? 15th. 15th. And we will have the usual quiz then. So hopefully everything went well with turning in and having the quiz yesterday. We're going to keep going with some more quantum mechanics today. We've covered photoelectric effect, we've covered the the Compton effect, and we're going to start now with talking a little bit about the uncertainty principle and a little bit more on the Bohr model of hydrogen. So we talked about the Bohr model and the idea that he approached it from a solar system point of view. Due to the basically not really knowing, right? Due to the advancements in the analysis of the spectrum. So Bohr came up with the idea of a relatively heavy, essentially initially he thought it was just make it stationary to make the analysis easier, nucleus, and then electrons going around the outside of it. Now, the nucleus was discovered in about 1911, which was about a year or two before Bohr's model came out. And the nucleus was discovered by Rutherford in about 1911. And the electrons were discovered by Thomson in about 1897. And so Bohr knew what the pieces of the atom were, and it was just the idea that they need to be arranged somehow such that they emit particular wavelengths when they are essentially de-exciting. All right, so I kind of drew on in class last time the solar system model, but let me show you a little bit more. If we draw the energy levels, hydrogen atom energy levels, these types of plots are very useful in the sense that you can think about what energy is necessary for the electron to move between two orbits, okay? I typically refer to this as the staircase model. Now, when you are walking up and down stairs, there is a particular place where you're gonna put your foot. You can't put your foot anywhere you want because you're gonna jar your back, essentially, right? If I decide my foot's gonna go, if the stair is here and I decide my foot's gonna go here, well, I can't have it stay there. It's gonna fall into where it's gonna be stable, okay? And basically the same is true for the hydrogen atom electron orbitals. They can't be anywhere, right? They're gonna be particular places. So we think of it spatially as the solar system model from the Bohr perspective, but from an energy point of view, you can think of it as, well, there's a ground state energy, which is down here, say. The ground state here we call n equal to 1. And then there's another state which is higher up above that. It's a staircase kind of like, right? And it's going to be up here, say here. This is the n equals 2 state. And this is known as the first excited state. And there is a particular energy which separates these two levels. Okay, there's definitely a 3-state. I skipped 1, 2, 3 here. So there's a 3-state. This is the second excited state. Here's the 4-state. Let's see here. I skipped 1. Here's the 5-state. 6. Okay, I'm trying to be very careful about how I'm drawing these levels because the spacing is decreasing between successive levels. And we'll talk about kind of how we know that in a few minutes. Now, Bohr's idea about how to describe the spectrum of hydrogen from an electron, from an atomic point of view, is basically as follows. He imagined that the electron has many places where it could go when you put energy into it. So if you think of the solar system model, right, our nucleus is heavy, and then there are particular orbits that the electron can have around the nucleus, like this. Okay, but it can't have any orbit it wants. It can only be one of these. Okay, and therefore those orbits particularly correspond to particular energy levels. So for example, you could say this is the n equals 1 state here. This is the n equal 2 state. Here's the n equal 3 state. And you could keep drawing further and further and further concentric circles. But from an energy standpoint, this is what we're thinking about. Right? The n equals 1 has the lowest energy. In other words, there's a negative charge really close to the positive charge of the nucleus. So it is the most tightly bound. One pretty straightforward question is, we know that positive charge and negative charge should be attracting each other. So what's to stop the electron from just sitting right on top of the nucleus? Why is the electron out a certain distance away from the nucleus and has some energy here when it could perhaps make its energy even lower by going and sitting right close to the nucleus? Okay, well, Bohr's answer initially was, well, it just doesn't do that. Because if it did, then all the electrons would be doing that and atoms would not exist, right? They would all have the electrons sitting right on top of the nucleus, and they would be stationary there, and there would be no need to think about what atoms are, because they would not be possible. So after a few years, after about a decade or so, a new line of thinking came up about, well, how come the electrons don't just sit right on top of the nucleus? And this was a question that needed to be resolved in order for people to kind of go forwards with it. The issue being that if you can't answer some of these questions with your ideas, well, then people don't really believe your ideas. So it took a while, but eventually the answer kind of came up with, and we'll also talk a little bit about this somewhat later today. The more technical answer to that question is given by what's known as the uncertainty principle. So we'll talk about that in a little while, but nonetheless, there is eventually an answer to this. So I'm like I said in the last class, I'm kind of pushing together a bunch of things pretty quickly in things that were spaced in time chronologically. We're kind of covering them all very quickly. So imagine that the staircase, right? The staircase of energies relates to the energies of these orbitals, and we simply do not allow the electron to take on any orbit it wishes. It cannot exist in here where the white space is. It can only exist on the circles. Therefore, it can only exist here where there's a step, and it can't be anywhere in between here because there's no place for it there, right? There's no place to put your foot. So you're gonna you're going to land on that one no matter what. I can't put my foot here and expect there to be a stable state here if I'm trying to walk up a staircase. So Bohr's Bohr's thinking was, look, I'm going to say a couple of things. Number one, the electron has particular places it can go, and that corresponds to particular energy levels. Number two, whenever an electron goes between these levels, a photon is emitted. So in other words, if, for example, an electron here in the n equals 3 state, how did it get there? Well, we'll talk about that later too. We put some energy in and excited it, and it's jumping down. It's jumping down into the n equals 2 state. Suppose it goes like that. When it does that, it's going to emit a photon. The photon, I'll just draw as that wavy line right there. I'll label it gamma, because that's a photon. Not that it's a gamma ray, not that it's a gamma frequency photon, just some photon. That photon would correspond to a drop in energy, which is essentially modeled by going from here to here, and when that happens, out goes the photon. Okay? And this is how the energy conservation maybe can be looked at, right? There's a higher energy here, there's a lower energy here, because when you get closer and closer to the nucleus is positively charged. The electron is negatively charged. So as it gets closer and closer, its energy goes down. The thinking behind that is the same exact idea as why do things go towards Earth's surface? Because that is where they have lower energy. Okay, so the electric charges which attract each other are going to want to attract each other and get closer and closer and closer. That makes their energy go down, 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 down. So, since this is a bound system, we have the convention of calling the energies negative, because you have to put in energy in order to rip them apart. So this is a less negative number going to a more negative number. All right? Therefore, the more negative number is technically lower in energy than the less negative number. Okay, so when it drops from here to here, it emits the photon, which is the difference in energy between these two energy levels, and that photon has a particular wavelength. The wavelength we can measure. If we measure the wavelength, we know its energy, therefore we know the energy between these two energy levels, and Bohr came along and said, okay, let's talk about the energy between the two energy levels. The energy levels and what he did in order to do this was I would say beautiful, but it's not really beautiful. It's just it's a really well put together set of arguments that really aren't true as we think of it now. But in those days, it was pretty solid. It was pretty good stuff. So he looked at the electron as having a centripetal force orbiting around the nucleus. And when you introduce the idea that there are only certain radii that are allowed, then that puts restrictions on, say, the orbital angular momentum it can have, and all these types of things, okay? I'm not going to go into the details of this. Suffice it to say that when all of this is said and done, Bohr was able to derive from essentially applying Newton's second law to an atom. He was able to derive that the energies of the electron levels were this number multiplied by 1 divided by n squared. And therefore, a transition between the two energy levels would require two of these indices, right? So if we call the level n, 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 n like that, so we'll call them like n initial and n final or something like that, or m and n also is used. But nonetheless, if I think about a delta E of the electron, then it comes to minus 13.6 EVs, and it would end up being the final minus the initial. So in this case, for example, I'm dropping from 3 to 2, so the 2 is the final state, and 3 is the initial state. So 13.6, 1 divided by n final squared minus 1 over n initial squared. In this case, I have the final being 4. And the initial being 3. The final being 4, 2 squared. And the final, subtract the initial, would be 1/4 minus 1/9. Okay. Notice this is going to give us a negative number. Okay. And it should, because the electron dropped in energy, right? It's up here where it has slightly higher energy, it's dropping to a lower energy. That energy difference, however, is showing up in the photon that is emitted between the two levels. Okay, well, during the transition between the two levels, say, all right? Therefore, if you think of it from an energy standpoint, what we could do, all right, is say that here in the 3 state, there's some amount of energy. Okay, you're in the 3 state. In the 3 state, there's a certain amount of energy. Now it drops to the 2 state, which has lower energy. And the rest of that energy is due to the photon. Okay, you'll find the rest of this energy in the gamma. And I know it's not a gamma. I just, I don't know, that's just what I call it. I'm not quite sure why. Okay, so the difference in these energies, right, it went from 3 to 2, which means I'm taking this number and subtracting that number. And that means that the leftover E of the photon should be equal to the negative of that difference in energy. Okay, so here what you'd say then is the photon energy is 13.6 with a positive times 1/4 minus 1/9. And this, by the way, is exactly what Rydberg came up with as a consequence of the Balmer analysis, which I talked about briefly last time, and that just came about from a wavelength analysis, right? Bohr is actually doing this from an energy and a mechanics point of view. So when you calculate this number, the 3 to 2 transition here, if I say, okay, what's this number? What we're going to do, let's see, what is this number? I don't remember this number off the top of my head. Let's take a quick look. This is 1/4 minus 1/9, and we're going to multiply by 13.6, and that's about say it's about 1.9. All right. Now we've using Bohr's formula, we've figured out what the energy difference in the electron levels is, and therefore what the energy of the photon is. So we have, in principle, calculated the energy. Let's now calculate what the wavelength would be with that energy. We know that the energy of the photon would be given by this. Therefore, the lambda here is the lambda from 3 to 2. And that looks like 1240 eV nanometers divided by 1.9. Can we call it 2? It's a little less than that, but it makes life a little bit easier. That way I don't have to worry about actually doing a division. And so this turns out to be 620. which, if you use the actual correct numbers, does match what the spectrum of hydrogen gives. Remember, the spectrum of hydrogen had only these 4 visible lines. One of them was red, and it would be a wavelength close to this, right? If you use the 1.9 or the 1. It comes out 1.888, blah, 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 right? And if you were really a little bit more careful with the numbers, you'd see. But the idea here is that Bohr has figured out what's causing the spectrum from an analysis involving an electron circulating around a proton and applying a few basically guessed at rules. All right, so this became the Bohr model of the hydrogen atom, and it was pretty successful at describing hydrogen. It was not successful at being applied to other atoms. The reason for that is because once you start getting to other atoms, 2 things happen. Number one, you have much more stuff in the nucleus. You have more protons, more neutrons, you have things going on in here. Okay. Well, it turns out you can kind of make the Bohr model, you can fix it so it works for heavier and heavier nuclei and heavier atoms. But the problem is, this only deals with a single electron. So whenever you go up in the periodic table and you want to use the Bohr model, you have to ionize everything away from it, and you strip away everything so you have only just a single electron left. And then you can talk about what the energy levels look like and what the spectrum would look like. Well, that's not so useful, right? That's not incredibly useful. So what you can also do is adopt a kind of another viewpoint, which I'll talk about in a little while, in which you have many electrons and you have many protons. You have a large, maybe copper or something like this, right? So you have all those protons in there, but if you want to concentrate on the very outermost electrons, those kind of act like Bohr electrons because of the amount of cancellation of the positive charge with all the negative charge that the outer electrons are able to see. So we'll talk about that later. But anyways, the point being here that this is a model which actually describes what the observed wavelengths are from the hydrogen atom. All right. So let's go through and calculate a couple of these. Let's look at it from another point of view. Let's take a look and say that, well, we know one of those wavelengths. Can we figure out what's going on with the electron if I know what one of the wavelengths is? All right, so the set of wavelengths was something like there was a 410, a 434, a 5 something or other, and a 6 something or other. So let's take the first one, because I know that one was 410. So let's take a look at this and say, all right, if I say, what does a 410 nanometer wavelength for a photon mean in terms of the hydrogen atom staircase? So let's start off by finding the energy of the 410 the 410 nanometer photon, which is observed in the hydrogen spectrum. And then let's try to find out, between what levels would this correspond to, between which levels would the electron be falling? In order to emit that photon. All right, so essentially this right here is our energy equation for the electron orbits. Oh, by the way, I use the word orbit and level interchangeably. To me, those mean the same thing. We're going to look at the photon energies as basically being the negative of this thing, right? Because of the energy conservation, which I just erased from over there, okay? So, If I want the photon energy, then all I gotta do is take away that minus sign, and I gotta look at the final minus the initial and figure out what I can from that. So the good news is we started off with a 3 to 2 transition, which was in the visible. And the 3 to 2 transition is a pretty small energy transition. Now, if I think about finding this energy, let's compare. Now, what do we expect to have happen to the energy of a 410 nanometer photon compared to a 621? What's the energy of that? I'm going to go over here and take away all this. All right, so let's start off with the energy of the 410 being equal to 1240 eV nanometers divided by 410 nanometers. Okay, this is going to be a particular number, and that number is by 410, about 3.02. electron volts, which is greater than the 2 that we just had. But what if we looked at a larger energy transition in order to try and find one that was slightly bigger? I don't need one that's hugely bigger. I need one that's only slightly bigger. All right, well, for example, if I thought about, well, what if I went from 4 to 3? Okay, well, problem is that wouldn't quite work, right? Because this is a 2 electron energy difference. 2 electron volt energy difference. And this is less than 2, because as you go up and up, the energy level spacing decreases. And you can kind of see that. Actually, you know what? Let's go do that with this. I erased this, which I shouldn't have. But let's go and do that real quick with the Bohr formula. Okay, this is the energy, this is the way you calculate the energy of the electron orbits. You just divide that 13.6 EVs, which was figured out by Rydberg, divide that by the square of the orbit number. So that means this energy is 13.6, well, negative 13.6, E1, the ground state energy. If I then go to the state 2 here and I divide the 13.6 by 4, I'm going to find that this is minus 3.4 EVs. Okay. Here E3 is, I believe that's actually negative 1.8, I can't quite remember, 13.6 divided by 9 is 1.51, that's right. 1.51. E4, let's do 13 divided by 16, and that's negative 0.85. We'll go to that one, more of 0.54. And lastly, number 6, which is, say, 0.38. Okay, so you can see that the transition from here to here is about 2, right? It's 1.5 to 3.4. Well, it's just exactly 1.9, right? So this really is the red transition in the hydrogen atom. Okay, but now look at this transition here. This transition was 2 EVs. Well, look at this one. This one's 10. This is 10 EVs. This is not visible. Remember, visible photons have energies of around 1, 2, 3, 4 maybe electron volts. Definitely not more than that. I mean, this is a 410 and it's at 3. So that's pretty much about as much energy as a visible photon will have. If you get to 10, you're definitely in the ultraviolet. All right, that's a big energy. Here we're at 2. Between 3 and 4, we're at about 0.7. Between 4 and 5, we're at about 0.3. Between 5 and 6, we're at about 0.2, 0.1517, almost 0.2. Right? So the spacing between the levels is decreasing because of this n squared here. Now, what we need to do is figure out, okay, I need something that's about 3. Well, this was 2. That was about 0.7. 0.4 to 0.54, that's pretty good. But if I go to 3.4 to 0.4, it's 0.38. This actually looks like the best option right here. Right? It's not enough to just go up 1 to 4, the 4 to 2 transition, because that only is going to give me, right? This is about 1.9 EVs, but this is going to be about, what, 2.6. And then this one's going to be about 2.9. But this one, right? This one looks pretty good. 3.02, that looks exactly like what I want. So that means that the 6 to 2 transition, okay, the 6 to 2 transition gives me a photon of that wavelength. Right? Delta E 6 to 2 would be final minus initial, and so that would be minus 3.4 EVs subtract, which is going to be end up being positive 0.38. Right? Yeah, indeed, this is negative 3.02. All right, which is exactly what we need for the photon. So we had those 4 visible transitions, remember? Well, here's 2 of them right here. Guess what, where the other 2 are? Okay, that's a 410 nanometer. If I think about the 5 to 2, that's the 434 transition, and I think about the 4 to 2, that would be the 5, I forget what that other wavelength is, but that would be the green line, right? Okay. Collectively, this set of drops that all end right here emit the visible spectrum. And since it was that was first, it was the visible spectrum that was first seen in hydrogen, this is known as the Balmer series. Okay, that's every transition from 6, 5, 4, 3 that ends at 2. Remember yesterday when we talked about the Rydberg formula, they were basically finding, I erased it from over here, but they were finding that it was always 1 over 2 squared minus something, and that something was 3, 4, 5, and 6. Well, this is the description of it, why that seems to work. Okay? So that's down to the genius of Bohr. Now, you can certainly talk about other energy levels and other energy transitions, because you can certainly talk about, well, why does it go 6 to 2? Why doesn't it go 6 to 1? Well, it turns out this is all just kind of a random process. But but the way I think about how do you get these transitions to happen is I go back to a staircase. Visually, this staircase for me is what I think about whenever I think about electron transitions. So how do I excite an atom in order to get it to emit wavelengths such that we can then analyze its spectrum? Well, if I think about the staircase right now, remember this staircase is not evenly spaced. It's big steps down here, small steps up here. So it does change. But if I imagine an actual staircase, then how do I get an electron up to the top of the staircase? Well, I throw it, okay? Well, I'm not gonna always, imagine you've got, what's a big, huge staircase, like the staircase up to like I don't know, Mount Fuji or something. There's a staircase up. There's a staircase up, or a staircase up to like Machu Picchu or something. There's stairs that go up some. That's a big long staircase. So you throw the ball. You might not be able to reach the top of the staircase, but it'll get up there. And then what will it do? It will bounce down and hit different stairs randomly. Well, then you're going to grab it again, throw it up there again, and it will probably hit different stairs because it will go to a different place. Basically, that is my mental picture of what we do in order to excite electrons in atoms. We put in energy into the electron. They're all initially down here in the ground state. Well, this is hydrogen, so there's only one of them. It's down here in the ground state. And we suddenly go, up you go! And it goes, whoa! And then starts going, doo-doo-doo-doo-doo-doo, back to the ground state. And then we go, up you go, and it goes, boom, and then it hits different states on the way down. Now, if you have a large collection, like a sample of gas, maybe you've got 10 to the 24th worth of atoms inside the gas canister, and that means when you shove them, when you give them a bunch of energy and they go up, they don't all go up to the same state, and they don't all fall down through the same states, which is why you see all of these lines at the same time, right? It's collectively, the atoms are making these transitions randomly. And one over there is doing the 4 to 2 transition, and one over there is also doing the 4 to 2 transition, and one over there is also doing the 4 to 2 transition, and those are all coming out as the same wavelength, so we see that in cyan, right? And this one's all doing the 3 to 2 transition, and that one over there is doing the 6 to 2. But that one over there is doing a 4 to 1. Oh, well, that one's jumping all the way from here to here. Well, that one we're not seeing visually. We can detect it, but we're not going to see it. Anything that ends down here is in the UV, okay? Because the energies are just so large. That's known as the Lyman series, because eventually in doing this, the equipment became good enough that people were eventually able to detect ultraviolet photons. All right, so let's calculate what that wavelength looks like. Let's calculate what that wavelength looks like if I go 4 to 1. How much space I got here? 4 to 1 transition is typically what I would call it. Not sure if am I still on the, oh, still got it. All right, good. All right, so we'll stay there. So let's find the wavelength of the 4 to 1 transition. All right, in order to find the wavelength, I have to go back and find out what the difference in the energy levels is. Once I find the difference in the energy levels, I go back to my HC over lambda, and I solve for lambda. Okay, so you can kind of streamline this process by putting those two steps together. Or you can just break it into 2 steps and do it that way. So the first thing is, if I find the delta E of the electrons, or I called this delta E 4 to 1, say, instead of that. This is the change in energy of the electron. I tabulated what all the numbers were. If I just kept it out as the Bohr formula here, I would have done 13.6 EVs times 1 over, where did I end? 1. And what did I start with? 4. So we'll do 4 squared and 1 squared. I'll put the squared in here just for smiles and giggles. Okay? I would say this for the electron energy difference. I would then say energy of the photon is equal to negative that number. In other words, just wipe away this negative right here and calculate it and you'd have it. And then I'd say that energy is hc over lambda. If I want the photon's wavelength, all I do is flop the energy with the wavelength. So now I'm going to get gamma 4 to 1. I'm going to get lambda 4 to 1 as being hc divided by the negative of the electron energy level change. Like so. Okay? So you can just kind of algebraically squish all this together so that it is a one-step process, if you like. What we'll do here is we'll say it's 1240 EV nanometers divided by, and then this process here is essentially 13.6 times oh, that's 0.16. I mean, that's a 16, so this is about 0.84. So if I go back to here, I would have said the transition is 13.6, and I got to add the 0.85, which makes it 12.4, 12.56. So let's say it's about 12. If I added 1, it would have been 12.6. So this is about 12.8. 12.8 EVs. Like I said, that's well out of our visual acuity. So let's take a quick look. This is what, 12? And this is, oops, divided by 12.8. No, wrong one. 1240 divided by 12.8. 96.8. 875, say 96.96, so let's say about 97. It's around 97 nanometers. All right, this is well into the UV. All right, well into the UV. Likewise, you would find the energies of the photons are small if you make, for example, a 6-to-4 transition or a 6-to-3 transition. All these different series with different ending points have names. The one ending in 1 is known as the Lyman series. 2 is the Balmer series. 3, I think, might be the Paschen series. 4 is the Brackett series. It's something like that. So you'll see eventually, you'll see these words which correspond to the names of the people who investigated these wavelengths. So Balmer, anytime you're talking about the Balmer, it ends in n equal to 2. The Lyman ends at n equal to 1. I think I said Paschen. I could be getting these backwards, and if so, I'm sorry. And then Brackett. And these end in n equal to 4. Let's see. I don't know if I have this written down somewhere or not. It's just the thing that you know. Okay, no, I don't necessarily see it. Alrighty, so this is how to calculate energies and wavelengths in the Bohr model. I mentioned that there is a way to fix up the Bohr model for heavier atoms as long as they are only carrying a single electron. And the way to do that is to multiply everything by that proton number. But I'm not sure if I want to go and do that right now. So what I do want to do, let's see here. Yeah, so here's what you can do. Let's do this here. Just make a note here that for heavier atoms, as long as they're singly ionized, not singly ionized, I'm sorry, only carrying a single electron, right? This is single electron only. You can kind of fix up the Bohr energies of the levels to be minus 13.6 EVs times 1 over n squared multiplied by z squared, where z is the number of protons that are characterizing the element. Right? That's the proton number, and it's squared. The reason for that is because the force exerted in the centripetal, if you go back to the Bohr model and think of the electrons circulating around the nucleus, the force is going to be relative to what the attraction between the negative and positive charges are. And so more protons means you're going to get a higher attraction. And the z squared comes in because of that. All right, so that's how to calculate energies and wavelengths in the hydrogen. And then if you wanted to go to further heavier, those single electron atoms, you could multiply by the z squared. And that should be about right. Okay. Now I'd like to go back a little bit and address the question of why doesn't the electron sit on top of the nucleus? And let's look at it from the formulation that was proposed by Heisenberg. And again, probably something you've heard of. Heisenberg realized that what was going on was there was a collision between these two models. There was the particle model and the wave model, and they both had their contributions to make to trying to describe what's going on with these quantum mechanical objects, right? Neither one is fully correct by itself. So what we do is we have to take bits of each one of them. And that leads to, as shown by Heisenberg, a fundamental uncertainty in things. And this is where interestingness starts. Well, maybe I don't know if it starts, but maybe it gets continued here. So Heisenberg's uncertainty is due to particle model and wave model. It essentially is exploring the limits of the two things. So I'll just diagram this out for you. I think this is probably the easiest way. Mathematically, to derive this is kind of a long and involved process, which I don't think we need to go through. The particle model, essentially, okay, there's a particle. Okay, you can barely see it. I made it really large so you can see it. I'll make it a little bit larger. Okay, there's my particle. Now, note this is not a mathematical point because otherwise you wouldn't be able to see it. But nevertheless, that's how we classify it in our heads. It's a mathematical point, and we give it the mass of the thing, right? That's our particle. The wave, let's see here. And I'm only going to draw a part of the wave here because I only have so much board space. But a mathematical wave goes off to infinity in both directions. Okay. Now, I don't have the time or space to draw that, so I'll just draw this portion of it right here and put some dots there. Okay. Now, here's what's going on. If you think about what is measurable about the particle model? If I took a snapshot, okay? If I took a snapshot, a picture of something, for example, you could go to a baseball game or something, right? And you took a picture of the baseball. You would be able to, probably through looking at relative positions of things, you'd probably be able to say approximately where the baseball is. You'd get a really good idea of its position, okay? Because it's a particle. Where is it? It's right there, right? Its position is well defined. Okay? It has a well-defined position. But in that snapshot, could you say what its velocity is? And you can't really. I mean, you probably could because it's a baseball game and you know the ball's going this way, that way, the other, right? It's not going, if it's a home run, it's probably not going back from the stands this way towards home plate. But it could be. You wouldn't be able to know if you just showed the thing to somebody who didn't know anything about baseball. They would say, well, I don't know which way that's traveling. Could be traveling straight towards you for all you know. Okay. It is therefore not possible to get a lot of information about which way is this going. Right? Therefore, we'd say there's no information about particles' velocity. Okay. Now, imagine it this way. Okay. You are in a completely dark room. There is a billiards table in front of you. Okay. In fact, you have your hands on the rail, so you know where the extent of the billiards table is, and you have been given a billiard ball, and you are told that on the billiards table there is another billiard ball. So how are you going to find out where the billiard ball is that's on the table? You have one in your hand. So I would suggest the most systematic way of doing it is to start at one end of the table and kind of throw the ball so it hits the opposite cushion and comes back, and you catch it. And if you didn't hear anything, then it wasn't there. And you move a little bit, and then you do the same thing that way, and then, nope, nothing here, crank. Oh, it was there. Okay, now where is it? We don't know. It's a fully dark room. So as soon as I hear it go crank, I knew where it was. I don't know where it is now because I have no information about what its velocity is or what its velocity was, right? When it got hit. I don't know how it got hit. My probe billiards ball is not returning to my hand. So I don't know where that went. It's gone. So I have no idea about the trajectories of these things. Okay. So I can tell you exactly where it was, or kind of pretty close to, yeah, it was right about there, but I have no idea where it is now. Okay, so I knew where it was. I have no idea where it is now because I don't know how it was traveling right after I hit it. That, in a nutshell, is how you look at electrons. How do you look at electrons? You shine light on them, but light is a stream of photons, and as we've shown, they can Compton scatter. They can hit the electron and disturb it, right? So I can tell you approximately, there's a good chance that I know that I can say, oh, that electron used to be right there because I just shined a light on it and it reflected the light, and so I could see it. This is a little bit of an exaggeration. Of course, you don't really see it, but you can imagine there's reflected light that I could detect and say, oh, the electron, I detected it, it was right there. Now who knows where it went because it got hit by a photon and it's gone somewhere else. So we have no idea where it is. Okay. So that was what the particle model comes into play. Now if I look at the wave model, what is really well defined about the wave model? Remember, this goes off to infinity on both sides. What's well defined about this is the wavelength. But remember, in the de Broglie, I wish I could say that in a nice, smooth way. De Broglie. In the de Broglie relationship, this tells us that there's a well-defined momentum. All right? So in this case, wavelength is well-defined because it's a mathematical wave. And that means that as it extends to infinity on both sides, the wavelength never changes. Right, it's very well defined. It's a well easily measured quantity. But we know that that implies that there's something going on with the momentum. That wave is carrying momentum. And it's well defined. Okay, therefore, it has a well defined momentum. However, when I turn to asking the question, where is this wave? just like I did here with the particle. Where is it? Well, it goes off to infinity on both sides, so you can't say, oh, it's here, because it's also there, and there. It's all over the place. The position is extremely not well defined. Position is not defined. So you see there's a crossover here between these two things. Because here the velocity, of course, is related to the momentum. And so we don't have information about its subsequent momentum. We know its position quite well. Here we have quite a lot of information about the momentum via the wavelength, but no information about the position, or say that there's a large uncertainty in where we would say, if I say the wave is there, but I got to go plus and minus on the infinity for the uncertainty in it, right? If I say the position of this thing is here, great, what's the momentum of it? I'd have to say it's plus or minus infinity, because it could be going any direction with any speed, and I have no idea. Okay? So this leads to a fundamental uncertainty, because these two models are completely at odds with each other. So if a situation comes along that has to use both of these things, now we have limits on our understanding of how we can measure these things, right? So what this means is, the uncertainties, which is kind of related to the standard deviations of the things, which I'll just use, say, delta x here. So typically this is the standard deviations. And the reason for that is because they're mathematically calculable. Standard deviation in position, you might write as delta x. And if it's in momentum, you might write it as delta p. And what this is saying is that you can't say for a quantum particle exactly where it is and exactly what it's doing with as much certainty as you like. There is a limit to how much certainty you can put into that statement. And Heisenberg, like I said, I'm going to skip the mathematical derivation of this because it's just kind of a little bit involved. But Heisenberg eventually came up with the idea that if you take these two uncertainties, they're going to be, and you multiply them, they're going to be greater than or equal to 1/2 h bar, where h bar is h, the Planck constant, divided by 2 pi. Okay. There also, as it turns out, is an energy-time uncertainty principle, which kind of goes along with this. I will simply state it without too much hoo-ha. This is the position momentum, as you can probably see. The energy-time formulation is exactly the same thing. There's an uncertainty in the energy. There's an uncertainty for how long it had that energy, and it's the exact same number, 1/2 h bar. Okay. Now, I will say that this is useful to think about and realize how it comes about. It's not usually well used these days, and we'll see why when we get into the more modern formulations. But now let's get back to the original question, which was, why doesn't the electron sit on top of the nucleus? Well, this provides us a bit of a reason. Because if it did, we would know both where it was to a pretty high degree of precision, and we would know that it wasn't moving to a pretty high degree of precision. And that degree of precision would violate the uncertainty principle. That gives it a well-known, in other words, low uncertainty precision, low uncertainty momentum and a low uncertainty position. Right? If it's sitting on top of the nucleus, it's not moving. So we would say that it has zero momentum, and we would be able to say that with pretty high certainty. We wouldn't say exactly where it was because the nucleus does have size to it. Nevertheless, that's a really small size. And so we would say that that's about equal to zero, and that's about equal to zero, and that violates the uncertainty principle. All right? So that's a way of thinking about why is this happening? What this does is it gives everything a minimum amount of energy that's necessary because nothing can be truly stationary in the quantum mechanical world. Okay, so notice if it's truly stationary, even if one of these is going to zero, I violated the uncertainty principle, unless the other one is infinity. Okay, so if I can measure the other one and say, well, this is an actual number, but this one's zero, well then this can't be, the quantum mechanics can't say, oh yeah, way to go. It's gonna say, no, you can't do that, right? So let's take a look at what goes on here. Suppose that, let's do an uncertainty calculation for a couple of different things. Let's take a look at suppose I have, here's an example. Suppose I have a 0.01 gram pellet. I don't know, something like that. And I've measured its uncertainty, I've measured its position carefully. Pellet has position. I've measured its position uncertainty to 0.5 microns. That's 0.5 times 10 to the minus 6th. Okay, so what would be the minimum uncertainties in the momentum and consequently in the velocity? Okay, with that knowledge of x. Alrighty. So let's take a look and figure this out. So if I have a delta x of 0.5 microns, my delta p at the very minimum, right? Notice that this is greater than or equal to. So let's just set it equal to because that's the minimum that we're going to get. And I'm going to swing the delta x underneath here and say that this is 1/2 of h bar divided by delta x. Okay. So 1/2. Now h bar is, like I said, Planck's constant over 2 pi. And if we're in like regular length units of meters, then I'm going to use this in the larger formulation of units, which is joule seconds. I'm going to divide this by 0.5 times 10 to the minus 6 meters. All right, so let's do a quick examination of the units here. Is this going to work out? Well, remember, once again, we did this last time. A joule is a Newton meter. So I can drop those meters off. That leaves me with Newton seconds, which comes into kilogram meters per second. So that should work out. If I do this looking for those types of units, it should be okay. So I'm going to do, let's see, 1.05. So that's times 2, and that's times 2. So why am I even bothering calculating this? This and this go away, because that's 1/2 divided by 1/2. And it's 10 to the minus 6 coming up here, so that's 10 to the minus 28. So this is 1.05 times 10 to the minus 28. Kilogram meters per second. Okay, so quantum mechanically, not a very useful limit. In other words, I can measure that to almost as much precision as I could possibly imagine. Okay, it has an uncertainty of 0.5 microns, which is pretty good already. But notice that the 6 is nothing compared to a 34. If I look for V, then what I'm looking at is delta P divided by mass. And that means I'm going to divide by the 0.01 grams, which means it is, that's 10 to the minus 2. So this would be 10 to the minus 5 kilograms. So that's that number divided by 10 to the minus 5 kilograms. Which puts us at 10 to the minus 23 in the velocity, or the speed, say. And that's in meters per second. So like I said, this is essentially, this casts no restriction on our ability to measure, even though we think we did pretty well with the position. This is ridiculously small for a speed, and hopefully you can see that. What if now I say I take an electron and I know that it's somewhere within an atom? Okay, so let's take the exact same situation and let's look at it from the perspective of now I don't know where it is, but there's an electron in this atom and an atomic size, say 0.1 of a nanometer. All right, same example, but now electron in an atom with delta X being, say, 0.1 nanometers. Okay, that's about the size of an atom or so. It would be about half an angstrom, which would be a 20th the size of the radius. So it's about a 20th of a nanometer. So this is, I mean, this is a big, right? This is big, but it's pretty good. So what would I do then? I would say, all right, delta P, once again, 1/2 h bar over delta x. Now I would use the h bar in electron volt seconds rather than joule seconds. Okay, so I'd say it's 1/2, and I don't remember this number off the top of my head. So let's see, what is it? It's 4.14 divided by. Yeah, it's about 6.5, 10 to the minus 14, say it's about 6.5 times 10 to the, or 6.6. Say it's about 6.6 times 10 to the minus, what was it, 4.14 10 to the minus, so minus 14. And that's going to be in EV seconds. And I'm going to divide this by, what did I just say? 0.1 nanometers. All right, so let's take a look at this. The seconds somewhat problematic, but I'm gonna throw a C in here to probably help this out a little bit. All right. This is a really, really tiny number, right? This is a number that's on the order of 10 to the minus 10. Of a meter. Okay, well, maybe, all right, you know what? I will go back to using the old units. Let's use the old one. It's set. So that's 1.05 10 to the minus 34 joule seconds. So now I'm going to get something in the momentum here that's going to look like half of that, which is about 0.5. So multiply by 10. 10 to the minus 10, let's just do that. So let's do, this is about 5 times 10 to the minus 23. But that's in, notice, this is in kilogram meters per second. Okay. What we would do is we want to convert that into something that's actually useful for an electron and an atom. Okay. If I think about what the velocity, well, think about the meter per second, right? I'm just going to go back and use the delta V now. what I'm going to do now is take that delta P, that's the minimum uncertainty in the momentum, divide by the mass of the electron. But look at what happens. This is something on the order of 10 to the minus 23. If I do the mass of the electron in kilograms, that's a number that's on the order of about 10 to the minus 30. So this number is on the order of 10 to the 7 meters per second. Okay, which basically means we don't have a lot of idea of about what it's doing. Okay, that's 0.1 light speed. And I've just confined it down to this type, just in an atom. So making these measurements has drastic impacts on what we are able to expect out of another, what's called conjugate measurement, right? These are conjugates. Because making one smaller has impact on the other one. Okay, well, that's gonna about do it for today, and I'm going to bid you farewell. Have a great weekend. Homework 8 is posted and has problems on photoelectric effect. It has problems on Compton scattering. It does actually have a problem on uncertainty principle. So should be able to get a pretty good start on most of that. And I will talk to you on Tuesday of next week. I have a couple of announcements, so before I let you go. Number one, if you have a lab kit, please start getting ready to mail those back to us, okay? We need those back because we are going to be using those kits again, and all of that equipment we need to be able to give to other students. So please start bringing those back in. If you are out of the area, please start mailing them back in. And if I'm not, we have all your checked out ones. So in about a week from now, right? This is going to be, next week is the second to last week. So I'm going to start checking to make sure that you've gotten these back. If we're not getting those back, then I'm not going to release grades, okay, until I get those lab kits back. So please make sure that those lab kits come back to us. We do need them to reuse for other students in other courses, okay? Much appreciated. And there will be no lab on Friday this week, as we are done with labs for the week, for the semester. That's it, okay? So please start mailing your lab kits back or returning them to Julia here in the stock room on campus. Have a great weekend, everybody, and I will see you back here on Tuesday. Ciao for now.